a CRC, Cooperative Research Centre. We undertake advanced R&D work with the national security community, so we've worked with a number of the departments and agencies some of you represent here today, focusing on advanced analytics to support your operational needs. But above and beyond the R&D work we do a lot of work in the education and training space. And some of you have been working with us on some of the work we're doing around data science competencies. Some of you are involved with some of our PhD students. We sponsor over 50 PhD students in the universities. And we also provide training to the general data science community, data analytics community. And today is an example of that, where we're lucky to have Professor Murli Viswanathan from the Carnegie Mellon University. And those of you who are in sort of the data science, computer science space will know that Carnegie Mellon University is one of the world leaders in these sorts of areas, in areas like machine learning, data science, etc. So we're very lucky to have Murli here today. He's going to try and demystify what data science is all about. So I'm sure all of you have heard quotes like data is the new oil, and machine learning and AI is going to power the world and things like that. And there is definitely an element of truth to all of that. But what Murli is going to do today is give you a bit of a thumbnail journey through what data science is all about, what some of those techniques are all about, demystifying some of that, and maybe breaking through some of the hype of that as well. So we're really pleased to have Murli here today. So Murli does a lot of research work in this space, in AI, machine learning, data science more broadly, as well as being involved with other consulting to industry. So he's an Accenture subject matter experts for analytics, as well as his prime role at CMU. So with that being said, I'll hand over to Murli. Please help yourself to the food, and after the presentation today, stick around and help us polish off the food. So thank you very much for coming on.
Thank you. So I'd like to welcome you all. Thank you for taking the time and coming down today. Hopefully I can give you something of interest before you leave. But before we start, let's kind of, wake up from that afternoon snooze period. Anybody has seen this in the news recent times? Yeah. So that's the first AI generated painting that's sold at Christie's for around $433,000. They expected it to sell at around $7,000. But it was generated by a kind of neural network called an adversarial network. I'll give you a little bit of information on what it is later on. But and as you can see, that's the signature of the algorithm that actually generated that image. And it was actually a collective, a group of 3 people who trialed the network and generated this image. But let's take a step back into the past. And anybody knows what this is? It suddenly looks like someone dressed up as a robot. Yeah. This is actually a real robot that existed. In fact, I was trying to give you a bit of an archival footage just to. So this is Star Wars -3. So Electro could actually count to 10 and recognize commands. So this was Westinghouse's robot, which also had a dog associated with it. 1939, I think. But it was pretty cool for 1939. And just to give you an idea of what we have now, though, you'll find it really interesting. And I also try to give you an idea of how difficult it is to do what the Boston Dynamics robots are doing right now. So this is the state of the art in robotics. So if there's something more cooler, please let me know, and I'll correct my understanding. So this is Atlas, which is this is the latest robot coming out of Boston Dynamics, and Atlas is pretty much autonomous in a number of things that it actually does. So it can autonomously navigate in an environment where the surface is unpredictable. So this is Atlas completely on its own. The reason I'm trying to bring this perspective in is because a lot of the data science that we're going to talk about today actually has its origins in AI and machine learning, the machine learning part of AI. So to make a machine learn it's about its environment and do things like this requires a tremendous amount of research and subsequent development. And a lot of the data science has been inspired by work that has gone into robotics. So I tell my students this is why we have Skynet.
Chasing the robots.
I'm visibly upset now. I need to stop it like this. What I'm trying to make is that it's the amount of I guess research and development that has to go into making a machine autonomously navigate its environment and do things like this is amazing. And a lot of those techniques have actually come down into the modern data science and machine learning space today. And so that's what I'm going to talk to you about as we spend the next hour together. So let's move on. So I would like to tell you about a little bit about data science. It's very introductory in nature, so please excuse me if you are data science experts here. I'll also try to bring a bit about the trends and tools today in data science. And finally close this with a bit of the hype surrounding data science, machine learning, AI, and all of that. I'd also like to highlight certain best practices that I've experienced personally in working with so many clients in the public sector as well as our industry partners. So you've all probably heard this thing that's repeated a million times. It's already data is the new oil, right? So I've added a little bit to that. The data is the new oil, but crude data won't do, right? So the point is, everyone says this, but most people don't have the data to work with in the first place, right? So a big challenge for many agencies that I've found is that data doesn't sit in one place, it's spread across, they don't know what they have. If they know what they have, they don't know how to bring it together. So once you solve all of that, then you've got beautiful data science tools that will do the job for you, right? But 80% of the effort goes into getting the data together and bringing it in the first place. So, and by that time your budget's out and then the project is shut down. So, so that's what I've seen in many projects within government and in South Australian government as well and in other places and in private sector as well. So without too much delay, let me move on. The other thing that I want to actually also try to talk to you about is that there are a lot of problems for which machine learning and AI don't work, right? And you just can't. I mean, there's a lot of I guess fake news out there about AI taking over the world very soon. But I think there's way more to go before anything like that comes close, right? So, so why talk about AI, machine learning, deep learning, and all of that? Because the modern data science, I guess, techniques that are applied and that you see in your smartphones and in your Google searches and in your voice natural language processing, to a big extent, they have their origins in AI. Right? And machine learning itself that you hear about so much in the news. In fact, Tom Mitchell, who actually chairs the machine learning department, the first machine learning department ever created at Carnegie Mellon. In fact, it's the first machine learning department ever created in the computer science space. He has a textbook on machine learning. And what they've done is they've actually studied the future of jobs. And they've actually studied around 2,200 job specifications. And they've tried to figure out which ones can actually be automated by machine learning. Right? And what they've discovered is, to a great extent, you can automate a part of those job descriptions, but it's kind of impossible to eliminate the human element in many of these things. Right? So I can give you a reference to that. It's very interesting. There's a study with MIT that they've just released recently. So it's a future of jobs report. Anyway, so going back to this, what you're seeing today is, thanks to rises in technology and storage space and mobile and IoT and all of that, you are seeing great strides in machine learning that have actually become, to an extent that you've got commodity tools sitting on your desktops that are capable of doing great kinds of analysis, right? So I'll try and go through some of these things. And then some of the most popular machine learning techniques out there they come under a category of techniques called as deep learning techniques, right? I'll talk about that as well. Now, this is something that many years back, the deep learning field was almost dead. It was destroyed by a couple of research papers written by earlier scientists who thought that you could only learn by creating a system that reasons with rules and with kind of calculus, and that reasons like humans do. Inductive learning, and especially black box type learning, that is learn like how humans do, was actually kind of frowned upon in the earlier days of machine learning. But what's happened is, in the last few years, with the rise in data generation and with big data tools, what we find now is that we have strong capabilities in being able to crunch volumes of data, so we can learn from large amounts of data and actually mimic some of our neural network, our neural learning processes. So, this is, everyone knows about this, so we don't even just skim through this. But the most recent chip that's on the latest iPhone can actually handle about 5 trillion operations per second, right? And it's AI capable and all of that. As you find everything, in the latest CES 2019, there's an AI capable toilet seat, right? Not really. I'm not sure if you need it, but they've just released one, and apparently you can voice activate it and get it to warm up the seat for you and do the washing, right? I'm sure it's good if your brothers are hogging the toilet. And if you can hack it, but people have come up with all these kinds of applications for AI. Some of them pretty useless, some of them quite useful. But one of the key reasons for the data issue is that that's the difference. I mean, in 1975, the 10 megabyte hard disk was $3,000, and now I can't get a 10 megabyte USB stick maybe. So bandwidth has, as you know, bandwidth has shot up in speed and all of that. So therefore, with the rise in technology and mobile devices and all of that, what you find now is that we are generating data at a crazy pace, right? So, for example, the Australian SCAR, as it's called, the Square Kilometre Array, currently is producing 5.2 terabytes of image data per second. In fact, what they're doing right now is actually, once this data is generated, they're actually shrinking it to 22 megabytes. So this 5.2 terabyte image data is actually on the run is actually reduced to a size of 22 megabytes and then processed. So and this is something that's going to not stop. There's a lot of with IoT, the Internet of Things, with mobile devices being connected, with the rise of low cost sensors that people can afford and use. The data explosion is not going to stop. It's going to get bigger and bigger, right? But one key thing that I think it's important to understand is people sometimes don't realize that a large extent of this data is unstructured, right? So while we talk about volumes of data, where does the volume come from? It comes from all these selfies that you post on, and all those things that are posted on social media take up a bulk of this data, right? When you come to enterprises, this is not the case, right? Many enterprises or many businesses can still be data poor in many ways, and they don't even realize that, right? So that's, I think, that's a key thing. I mean, if your starting point is now and you are setting up a data infrastructure to collect data and then use it in the future, yeah, that's great. I mean, because you're starting at a best time, you can actually set up low-cost infrastructure to do it. But if you're from the 70s and 80s, you simply might not have enough data to come up with valuable decision-making knowledge in there. So a lot of this data, that while it's out there, it's not necessarily data that's business-friendly. That's my key take here. Now, this is something, again, that is very basic that we talk about when we talk about data, is that data has several characteristics that you have to contend with. Some of these characteristics make or break your project, right? For example, if you're talking about, if you have a situation where your business relies on streaming data, where the data velocity is high, right? Then you need to actually have an infrastructure that can deal with this streaming data. If you're not ready to do that, then sorry, you're not going to be successful in that endeavor, right? So likewise, one of the biggest issues that we as machine learning researchers face is that there's the uncertainty in the data, right? How do you data that's inherently noisy? How do you come up with some useful insights in the presence of noise in the data, right? Additionally, there's lots of different forms of data. So there's structured and unstructured data. There's a lot of multimedia data sources out there. And how do you integrate knowledge from all these different sources, right? I mean, you find that there are tools that exist for structured data. There are some tools that exist for unstructured data. But how do you combine them together, right? So those are still challenges. Then there's obviously data that's just sheer volume, right? And don't have the capacity to deal with the volume of data. So there are several aspects, and I think in all honesty, these are, if you're able to deal with all these issues, you've actually you've solved like 75% of the problem. For many businesses, this is where the problem lies in, right? So data might be simply spread across, fragmented. Then they don't have a knowledge of the whole of enterprise kind of view. So all those things take up a lot of time to get right, and then you can think about applying data science techniques or machine learning or even AI-based approaches. Yet another kind of data source kind of description. So for example, when you talk about different kinds of data, for example, when we talk about sensor data, the velocity of sensor data is really high because you're generating massive amounts of data. Variety can be, again, varied, volume can be high, and depending on what type of data it is, whether it's structured or unstructured, varies in complexity as well. So, but when you talk about, I guess, business apps, when you talk about enterprise documentation, then things change to a great extent. I mean, you might have a variety of data in your enterprise, but you might not necessarily have the volume that you need for analysis, right? Or the volumes are probably not as high. So, so for a data scientist, right, if you are put in a position where you've got to work on a project, you've actually got to have an understanding of this, right? What am I dealing with here in terms of the data sources, and what do I need to do with them, right, to handle them. So the data wrangling part is kind of, and just to take you on from there, LinkedIn sort of does studies on their top hottest skills for different years. I think they also put their top jobs as well. So in the last 4 years, their top 2 hot skills have been cloud and data mining, right? And as you can see, you can fill in the blanks here. This still has been data science. The top one has been cloud and distributed, becomes a skill set. And I was recently studying a jobs report, and the average starting salary for data scientists in the US now is at least 100, but it goes above that, much above that. So it's the reason for that is there is a shortage, because the data scientist is a peculiar kind of character, right? Because the skills that you need for a data scientist are kind of, I don't know, it's very hard to define, right? I'm struggling to say that, but one, you need to understand, you need to have pure data science skills, right? These include, I guess, so reasonably sophisticated computer science and data wrangling skills. But then you can't stop at that, because no data scientist understands the domain unless you are from that domain, right? I mean, I have no idea of financial services. So if I'm asked to work, in developing an algorithm for a financial services data science project, I'm not going to be able to do it, because I have to have a reasonable understanding of the domain, right? Because let me put this to you: you are trying to develop an algorithm that is going to learn from data from a domain, right? So you're building a learning machine. How can you build a machine if you don't understand how the domain itself is, right? So for a data scientist, the biggest challenge is that a particular project might be based on healthcare, while another one is on financial services. Yet another project might be helping a legal team develop an algorithm for scanning documents and things like that. So all of these domains have their own expertise, that you have to have an understanding of, right? So that's why the data science position is quite a challenging one to fill, right? And so having said that, let me just go through the usual, I guess, definition of not just data science, but this is basically what we're trying to achieve through the data science process, right? So from my side, so if you're given quality data, and this is why I put this right up there, that here you have the data is the oil here, right? But you just can't feed in crude oils, because that's not going to work here. You need to actually have a certain amount of curation done to this data in order to achieve, at the end of the day, valid, useful, unexpected, and understandable insights from the data, right? So unless you have that quality in the data available to you, these are not going to be exactly what you want, right? And data science itself today is actually, as you can see, it's not just a single discipline. It is a cross-fertilization of several different domains. So there's the domain expertise that a person needs to have. There's the computer science skill set, the data engineering skill set, and then the math aspect of it, right? So you really have to combine all of these, and that goes into the data science professional. Yeah. So that's the goal. Ultimately, what we want to do is we want to discuss knowledge insights from our data sources that can give us valid understanding or valid knowledge about where our particular business is going, or help us understand what has happened in the past, so that we can make predictive decisions about the future, right? So that's the ultimate goal of our data science process. In terms of now, what I find is that earlier in the early days, things used to be called simply as machine learning, right? And then people coined the word data mining, and now you have this word called analytics, right? And there are yet other terms that keep coming up. I guess just to make the field more attractive, or just, I don't know, they're reinventing the same thing again. But there are new terms that keep coming up. But ultimately, the goal behind even the machine learning approaches is basically to try and look at maybe three areas, right? One is trying to describe what happened in the past, or trying to make sense of that, right? So, it's often called descriptive analytics, as to try and get an understanding of what has happened, right? Predictive analytics, on the other hand, is trying to predict the future, essentially learn from the past and try to predict your future. What is going to happen in the future, with my business, or forecasting to a certain extent. And then lastly, we have prescriptive analytics that is trying to say, how can I take what I've actually learned and then embed it into my business, right? So it becomes a prescription, it's running in my business now, it's a part of my transactional system, right? And I've got it going. So all of our data science work is basically in trying to cover these three aspects, and that's what we learn about. And we learn different techniques, we learn different data wrangling techniques, machine learning techniques that we can apply to get an understanding of what has happened, or try and come up with a predictive model for the future, or try and even then build it into our systems in some way, right? Program it. Just a quick kind of useful example that I wanted to share. So this is an interesting thing in law enforcement. So in the US, for example, you find that there's a reasonable kind of I guess a reasonable amount of machine learning or predictive analytics in law enforcement. So several police departments across the US states have various levels of data science in law enforcement. So these are some of the examples. I was I was doing a presentation which had a law focus, so this is one of the examples that I used. But for example, Memphis police analyzed their crime history to effectively deploy police officers. Miami-Dade has, again, they've had a sophisticated level of machine learning embedded into their process. They were able to break several cold cases as a result of data science work. Durham police, again, they were able to basically uncover hidden connections and intelligence for proactive police action and so on and so forth, proactive policing and so on. So this is a small kind of video as to highlight this. If you want to kind of show, it's just 3 minutes.
Police Department services a population of approximately 2 million. We have major sports teams, we have major events, we have cruise industry. There's a lot of requests for services, a lot of requests in our resources. The Crime Data Warehouse supports and contains all incident reports, all costs of service, all crimes reported, all information reports. So we gather information gathered by investigators, supplemental reports. It is the brain that contains all the information that we have in the police department. We were one of the pioneers, one of the first agencies that created a crime data warehouse. My supervisors and my command staff have always been visionaries, and our police department is visionary to a certain extent. The IBM team partnered with us, and we created a team, and how can we tackle this project from a holistic point of view instead of from one person? We generate a lot of information. We generate a lot of reports, which is why we started with IBM and trying to provide a solution to analyze that information, to help our investigators gather that information quicker and faster. The solution we came up with is Blue Palms. It's predictive analytics lead modeling software. We put all the information from the crime data warehouse into this program. And it has a historical knowledge of all the incidents that ever occurred. When you ask it a question, it gives you the answer. And within a minute, have 20 potential suspects that could have committed the crime based on historical information and the method of the operation of the individual that committed the crime. This is not science fiction. It has to be fact-based because we're going to use this information in prosecutions and locating and identifying individuals that committed a serious offense. The analyst can now provide the investigator with a potential answer to a question that they couldn't answer earlier. When we endeavored into the program, our IBM partner was given 40 cases that we successfully concluded. And we took those cases and we ran it against the program as a proof of concept, where we had a 73% success rate. 29 out of 40 cases have successfully identified the offender as committing the crime. In the past, our analysts would look this information up following trends or at a request of the investigator. This information can be gathered and deciphered and analyzed, and it would take an analyst maybe several days. What this product offers us is a solution and an answer most of the time within a minute of the request. We're going to save money, we're going to save resources, and we're going to catch the offender quicker. And we're now realizing the power of the program, the power of analytics, and we're having conversations we haven't had previously. We had a vision, we thought we could get there, and we did. And now all those people that were formerly resisting the idea are all behind it and pushing us to get to the next step. They were excited that we were going to produce, frankly, a program that did not only help us, but we're thinking about regional. If it works in South Florida, why can't it work in the rest of the country? And that's the mission that we had, that's the mindset that we have and continue to have.
So I'm sort of not a marketer for IBM, so this is like an IBM kind of solution. But I think it's a successful application of how you can actually do analytics. This is one of the case studies that, and if you're looking at a successful story of data science in crime, I guess in crime prevention or crime or policing, I think these are some of the really good examples that you can go for. Right? There are many of them that haven't worked. But I think this kind of tells you what you have to do with the client in order to get them to actually give you the data in order to work with resistance to the solution, and then to actually come up with a successful end-to-end product. So I just wanted to give you an example before we get into the actually nitty-gritties of data science as such. So as I said earlier, data science itself is is multidisciplinary, right? And to a great extent, you find that data science techniques have come from across different areas. So you have a number of things that we teach in data science today are from AI, from statistics, from management sciences, visualization, databases, and machine learning, and a number of and pattern recognition. So we'll try and understand some of these things as we go along. But one of the key things that we can't not mention is AI, right? So a lot of the data science techniques that we see being used today, be it your AI on your mobile phones, for example, right? Smart image. I think a number of the new mobile phones that you see have an AI-based assist that helps you take better pictures. A number of techniques, even on desktop software, are now AI-enabled. A lot of applications are coming through which are essentially from some of these techniques, from some of these areas that have led to giving us approaches that we can now automate. Right? So, image recognition, machine vision. This is an area of artificial intelligence trying to make image recognition work, trying to make machines recognize the environment, right? And now you find that, for example, I read a recent news story about video cameras that have embedded facial recognition in them, which have been deployed in China, for example, across stations and across public areas. And the accuracy of image recognition in these video cameras is quite surprising if you look at how good they are. This was probably 10-15 years back this was impossible, but now you see with deep learning and neural networks, the image recognition accuracy has shot up by leaps and bounds, right? And this is now commodity. I mean, you can actually go on eBay and buy yourself a low-priced video camera that has built-in image recognition, right? So we have to thank a lot of research in AI for some, and some of these techniques are actually going into data science in order to try and work with structured data. And then we have things like natural language processing. So I don't know if you've tried voice recognition on your mobile phones about 15 years back, right? And if you can compare the accuracy today, again, leaps and bounds thanks to research in NLP and voice processing. I'm going to talk to you about classification and clustering and those kinds of things. But what I wanted to highlight is that AI has been instrumental in driving data science, or getting data science to the point where it is today, and it has actually become almost a commodity-based system now. You can buy so many data science products off the shelves and use them in analyzing your data. Right? So ultimately, the goal was to actually make machines learn, reason, problem solve, have a perception about their environment and understand language. Right? These were the early goals of AI, is to have an autonomous agent that can do all of these things. And a lot of the techniques that we're seeing used in businesses have come from this kind of endeavor. So I'm going to try and tell you or give you a primer on data science. And this is one of the most popular business models applied to data mining or data science in general, right? So what I wanted to highlight here is data science is actually a process, right? It's not just a single step. It's a process of looking at a business or looking at an enterprise or looking at a government agency, understanding their business, understanding their data, and then going through a process of preparing the data, modeling it based on the questions you're trying to answer, evaluating the models, and then after a series of evaluations, deploying it once you trust the model. Okay? So a typical data science project actually goes through all these phases, and without any of these aspects, for example, like business understanding or data understanding, the rest of the steps actually don't work. Right? So I'm just trying to highlight that while it sounds like something simple, here's a nice Excel spreadsheet, let's analyze it and produce some insights. In reality, that's not the case, right? So you actually have to go through these phases, and each of these phases is involved to a great extent in terms of coming up with the final product or coming up with these final insights or the final models that can predict the future or can give you improve your business ROI or improve your customer service and all of that. So, and the realistic sort of scenario is that by the time you get to the data preparation part, that kind of takes up, probably 70 to 80% of your project time, and also budgets in many cases. Because the reality is also that for many agencies and enterprises, their data is actually fragmented and spread across the agencies, and many people really don't understand where they can actually source the data from, right? So essentially these are the 6 phases in a typical data science process or data science project, where you have to understand the business. So given that you want to try and apply some of these data science techniques, you have to, typically your business, the consultant needs to understand your business. What is it that you're trying to answer? What are you trying to predict here, right? Once you have an understanding of that, then you can think about data understanding. Do we have the data to answer this particular question, or do we have the data from which we can actually generate a predictive model? Right? Once you have an understanding of the data, then you can think about actually getting it out. And for many agencies, getting it out takes a lot of time. That integration is one of the biggest challenges for many agencies. Right? What about if you don't have enough data? How about sourcing external data? That can be another challenge. So once you get to this point, then you can, and you've got this curated, and you've got it stored in a data warehouse, or you've got it stored in a nice database which you can access, then you can think about applying different modeling techniques depending on what you're trying to do. Are you trying to explain the past, or are you trying to predict the future? Depending on that, you can choose a variety of machine learning techniques that are available to you for analyzing this data. Right? Are we done here? Unfortunately not, because you need to evaluate the models. Right? You need to test how good these models are in terms of their predictive capabilities. Are they actually predicting with a reasonable amount of accuracy? Like what you saw with the Miami-Dade Police Department was that they had a 73% accuracy in terms of evaluating the models that were generated by the system. Is that good enough? When in a healthcare system, that might not be enough. Right? You might need much more accuracy. So once you're happy with the evaluation, then you can think about deploying that solution, deploying the model that you've actually learned. Right? So these are the phases and the tasks, right? But having said that, data science today is everywhere, right? You see, companies like Uber using it. You see companies. You see a variety of healthcare areas where machine learning is big. Not that it's actually used in practice, but it's quite big, right? So, for example, I was reading a recent article on using image recognition for going through radiological examinations, right? So there's a statistic that in China there's about 1.4 billion radiological examinations that happen over a monthly period, and if they could automate that for identifying things like tumors or automated identification of certain kinds of, malignancies that can show up on radiological images. And there's a system, they've actually invested in several systems that are now able to identify certain specific kinds of tumors and cancers on X-rays and on other films. And the accuracy rates are as high as 90%. In fact, they've done a study with radiologists versus this deep learning system, and they found that in many of these cases, the deep learning system actually works much better than the radiologists actually trying to identify these specific cases of tumors. So it's big in healthcare. Not just that, I think there's a lot of work on machine learning in trying to actually trying to predict hospital readmissions, for example. So there's a lot of case studies that you'll find on machine learning applications in hospital management, patient readmissions, the success stories on drug usage, and all of that. So it's big. Sports analytics is in the news all the time, and legal enforcement is big. And this is where I'll probably, before I finish, I'll talk about some of the issues or challenges that we face with machine learning today in terms of bias and prejudice that algorithms can also have. So there's this interesting news from Amazon. So Amazon, a couple of years back, they wanted to build an automatic resume analysis system. So it would be a machine learning algorithm that scans all the resumes and trying to see if it should actually give someone a job or not. So what they found was they had to train this algorithm on the past data. So they actually trained it on all the Amazon employees they had. And Amazon was so gender imbalanced that the algorithms rejected any CV that had a reference to women on it. So if it had women's college, it would be immediately rejected. So they actually got rid of the system. You can Google it. So and this is one of the issues that we face today with algorithmic bias. There's a big case study on an algorithm that is actually used in the US to try and, I think, prosecute repeat offenders. And there's a big controversy about, again, depending on the past data, which is kind of, I guess, biased towards African American, the algorithm basically takes the bias also, and the bias was found to be repeated within the algorithm. So there's a number of different things. I just read a paper a couple of weeks back about some researchers who've shown that algorithms can also generate prejudice by themselves if they're trained to do that. So they can copy prejudice as well, along with other good things. So that's the biggest concern that I have, and probably many people have in machine learning, is that how do you trust the algorithm, to not have those kinds of inherent biases? And you have to understand that essentially this is an inductive learning process. You're learning from past data. If your past data is biased towards a specific type of individual, then the system basically is good about that particular individual, but does bad at other kinds of things, right? Even with Google Images, I think a while back BBC had this news about what is a perfect face, and it was almost always going to be white, because the volume of images online is basically biased towards a particular kind of face, right? So the concept of a beautiful face is always going to be biased if you get an algorithm to put it out, because of the training that it's gone through with the images that are online. So how do you kind of build an algorithm to beat the bias? And that's where you need to and that's where what people are saying now is you actually need to combine. Just data science is not good enough. You can't use these automated data analysis algorithms to give you a predictive model. You have to combine that with some form of symbolic reasoning, where a human set of rules can actually be added on to the model that has been learned from the data. So adjustments have to be done. So a lot of different applications, right? So data science is everywhere today. You'll find that in every field where you find data, there are applications for data science, right? All it requires is a domain expert to think that I've got some data, I need a predictive model, or I need a way of gaining insights from this data. What can I do, and where can I find some techniques? And they're out there that you can use, right? So you find across the board in several different domains, there's a large number of applications out there. For example, in media and telecommunications, one of the very common kind of predictive analytics application is customer scoring, right? So giving every customer a value based on their past history with your organization. It's very common. Fraud detection, prevention, churn prevention, is very common even in companies that are trying to predict if employees are going to jump ship or leave the company, right? How can we predict that based on past employee profiles? So a large number of applications out there. What you're finding is there are a lot of other kinds of applications that are entering this domain, like sentiment analysis. I'll talk about that in a minute. But it is out there, and as Tom Mitchell says, machine learning has become a general purpose technology today, because the application is huge. If you're coming from if you're planning to work with data science, it's a good idea to understand that data science is a part of a larger ecosystem, right? What we call as data science, it actually includes the data aspect, the data engineering aspect also, right? And that's something that people sometimes don't realize. So, even before you can analyze your data, I think the important thing is to think about where does your data lie, right? Or can I actually analyze my data from where it sits, or do I need to bring it together, right? So that's where this ecosystem, or this common environment for data science is important. So often in the past, in the traditional data warehousing situations, what would happen is an organization would say that I want to analyze a particular part of my business. Should I take a snapshot of the data and bring it to a data warehouse and run my analysis on the data warehouse, right? But that whole scenario today has changed. What you find today is with modern database systems, you can do both transaction processing as well as analysis both at the same time, right? that divide between I have one database for my day-to-day transactions and another separate data warehouse for analysis, that's actually slowly going out. I think rightfully so, because with modern database technology, you don't need to separate the data. The data can sit in there. Systems are sophisticated enough to actually run advanced analysis on your transactional data, right, based on the time periods that you want to. So this is a typical kind of system, and I just want you to keep that in mind. So going through a few techniques very quickly, right? So I just wanted to highlight some of the commonly used data mining techniques in the data science process. So I just wanted to highlight that one of the most common things that you'll find people use when they're actually analyzing data is a technique called as classification learning, or simply classification, right? And the goal there is that given that I have these two classes, right? So consider the blue balls as a particular category of things. So it could be patients diagnosed with a particular disease, and green could be patients who are clear of the disease. So the question is that given a new data point, what is its class? Is it so if this was the x and y axis, or if each of these points was a vector, right? Think about it as having a lot of attributes and then a class value, right? Question is what should this be classified as? Is this a green dot, or should I give it green, or should I give it a blue color? Right? So what do you think naturally? I mean, from looking at it, it looks very simple. So why blue? Sorry?
There's more of them?
There's more of them. That's a good point. Any other thing? Why blue? Yeah.
It looks as though the sort of central point of all blue light is nearer to that than the central point of all green.
Yeah, exactly. So this is another heuristic, right? So that's what machine learning researchers do. They want to figure out what is the best class. So one way of saying it is because there's more blues, this has got to be blue, right? So it's basically using the majority principle, right? If I see 100 black crows, and if I see 3 white crows, what's the next crow going to be in terms of the color? Black, because I've seen mostly black, right? So, but this is a very common learning heuristic that we can actually apply, and there are many such techniques. So what you find that the machine learning and data science field is full of these kinds of techniques. There are, I would say, around 160, 70 different algorithms that all work on different kinds of principles of learning. So the simplest one that you said was because there's more of them, let's make this white dot a blue. Let's say this person is diagnosed with the disease, right? So these could be the attributes that you measure in order to predict the class. And based on what you've seen, we've decided that this white should be a blue dot, right? But what are the risks in this process? That you get it wrong, right? So you diagnose this person wrongly, and so as a result you make a mistake, right? And so what would be like? We would like to have a model that has a great level of accuracy, right? So makes very little mistakes in diagnosing the disease, right? So we need to actually, so we have several different approaches which come from statistical learning. There are decision tree based algorithms that produce decision trees automatically from large amounts of data. There are black box kind of algorithms that are called neural networks, and what these do is give a lot of training examples. So we call each one of these dots is an example, right? So what we're doing is we have an algorithm that we're going to train with examples. These are pre-classified examples because I know that these guys are all the blue ones are people who have been diagnosed with the disease in the past, and the green ones have not. So these are pre-classified examples. So it's also called supervised learning because we are supervising the algorithm to learn from this data and come up with a model to predict a new instance in the future, right? So essentially what we're doing is something like this. You're the tax office and you've got a big database like this, and these are examples that we have seen in the past, right? So what we want to do is take these examples. We want to basically say, look, let me take this example, take a chunk of this example. So let's say I have 10 examples. Let me take about 7. And let me call this subset a training set. And let me actually learn a classifier, right? So what do I want to classify here? I want to classify an individual as either a person who has committed a tax fraud or not, right? So I want to learn a predictive model, and then in the future, what I'll do is I'll use my model to predict if a new person is going to be a tax fraud or not. Right? That's my goal, is to learn this model that can predict a person. So the question is, what is the answer for these guys? That's what I want, right? So now in this process, it's really important to know that why am I only using a subsection of this data? Right? Because I want to test my model on a subset of data, right? Because if I use all my data to learn, how am I going to evaluate my model, right? I can't evaluate it on new cases, because then these are the people who are actually my new customers. So in order to check how accurate my model is, I break the data into the training set and test set, right? So I know the answers here already. So I can compare it with what the model says is the answer, right? So I get an understanding, or I get an estimate for this model's accuracy, and that is the estimate of how good the model is at predicting a person as a tax fraud or not, right? So this is the process of classification, and this is by far one of the most popular techniques that are used out there. For example, you go to a bank, you apply for a home loan, your information is processed by the bank's algorithm and already decided whether you should be given a loan and what is the range at which you should be given a loan. So there's an algorithm that already predicts if you're going to be a good customer and basically what should be your loan amount as well, right? And that is basically an example of classification. From the past, history analyzed and then come up with a model, and the model used to actually decide, right? And this classification is used in image recognition as well. How do I classify an image as a good one versus a bad one, right? So in my first slide, you saw the AI generated image. The way the AI generated image was created was that the algorithm was trained on around 50 or 60,000 images that are supposed to be images, good images, right? So and then the algorithm is asked to generate images like those images, right? And then there's another part, a subset of the algorithm that checks to see if this is a good image or not. So and then basically throws ones which, where the face is actually stuck on the hand or something, and throws those kinds of images out. Tries to find one that is a clear representation of what a human face is like, right? So the key thing here is the training. That is, the more data you have, the better model that you are going to eventually have, right? That's the goal here. The challenge is, what about if you don't have enough data? Yeah, that's where the model then is going to not be as accurate as you would expect, right? So very simple kind of heuristic. Now, in addition to that, I just want to highlight there are many other things, but we don't have time for all of that. But please remember that data can be of various types, right? So we talk about data that's discrete, data that's numeric, data that can be incomplete, noisy, all those kinds of things. So your algorithm will be smart enough to deal with all of that, right? Missing values, noise, values that are of all kinds of types, and then work in the presence of this kind of scenario. So that's one of the common techniques in data science that's used. Another one that's used as commonly as well is something called as clustering. So you are given, you've collected a million records for customers from who go to a supermarket. So you have a million records from supermarket customers. You don't know, they're not pre-classified. You've not categorized them as anything, good customers, bad customers, or customers. You've not assigned any value to them whatsoever, right? You've got a distribution or a spread of these customers. You're basically plotting them based on some attributes. It could be spending, could be income versus spending, or it could be a vector of attribute values, right? You're just plotting them and you spread them across, right? Now the question is, you want to try and identify, are there some natural groupings in this spread, right? So let's say you've spread these customers out and they look like this, right? So how many groups do you think there might be in this data? So I've just identified, I've just drawn this around this, right? Could you kind of guess why I've drawn this around that? Yeah? Because they're all together, right? So in geometric space, they look close. Right? So maybe they have something. I mean, they're similar in some way, right? How many other groups are there? Maybe this is another group, right? Or maybe these guys are another group, or maybe there's even 4. Maybe this is another group, right? But that's what clustering or unsupervised learning is all about. That is, we don't have an idea about categories up front. We're trying to actually impose categories on them, right? For example, I might group these guys together and call them as high-value customers, right? Based on some characteristics that I think these guys have. So, with unsupervised learning, our goal is to try and identify or the classes themselves or find categories in data, right? And the best examples of that are species classification, right? How do you classify species together? Right? So grouping of items and coming up with the classes themselves. Right? So that's the clustering definition. I'll leave that. And the other kind of very commonly used commercial technique is association rule discovery. That is typically applied on data that is supermarket data. So for example, each one of these records is a basket of goods, and what we want is to come up with the rules of this format, where these rules indicate strong associations of some kind, right? So basically, if again, this is kind of an urban legend, or I don't know what it is, but it's often quoted. Have you heard about this? So this is, I think there's a story that when Walmart applied this to their data warehouse, they found that when men on Fridays purchased diapers and milk, beer was the next popular product. So I don't know how true it is, but it's often quoted. So, but the goal is to try and find associations between values, and then essentially, then depending upon these associations, you use them for a purpose that you can identify. Right? And within the data science, I've spoken to you about these 3 approaches, which are, so when we look at these 3 approaches, typically what you find here are these approaches, they're essentially what I call as Whitebox approaches. The model is visible to us, right? For example, you can read this and you can try and identify what is the model telling us. It's telling us that there's a strong association between milk and Coke. There's a strong association between diaper, milk, and beer, right? So many of these models that we talk about for classification and clustering, these models are what we call as Whitebox or symbolic models, where we can actually explain the model that has been learned from the data, right? Another group of techniques that have been invented, which are very popular today, for certain kinds of applications, are basically what are called as neural networks. And there are varieties of neural networks which are good at certain things. And so, can you guess which person is real in this? So these there's images of, these images are of individuals. Some of them may not exist. They're just AI creations. I won't waste your time. None of them are real. None of them exist. Right? They're all unreal. They've all been created by an AI software that has been given by a deep learning network that has been given images of celebrities of all sorts. Right? So what a typical neural network does is it has an ability to extract features from data, right, and then use those features to discriminate and identify newer or classify new examples, right? Or it has also been used in generating new examples of the old type, of the past, right? So these images are what the neural network thinks are celebrities, but they don't actually exist. But this is what it has generated after several simulations running through that network. You can actually see that it's not perfect, right? You see the eyes? So this is another thing that you probably heard about deepfakes, right? So deepfakes are basically videos of people that, again, are AI generated. So they're AI generated videos of people that don't exist, or there are ways of actually taking a person's face and then embedding it into something else and getting a really bad or good video happening, right? So, so recently at Carnegie Mellon, a bunch of researchers have actually created a technique that actually transforms the content of one video into the style of another, right? So you can take a person speaking, actually overlay the video on someone else without, obviously, being able to figure out what was the original version, right? So they've produced several videos of Obama speaking in the form of Trump and all of that. So you can actually Google that and have a look. But these are some of the advances that have been possible through neural networks. But neural networks rely on a large amount of data. At least certain kinds of neural networks that need to learn from the data, right, require large quantities of data, or they go through a problem called overfitting. That is, making optimistic predictions about the future, and as a result, making mistakes, right? So, neural networks are black box techniques, meaning the model that the neural network learns is very difficult or near impossible to explain, right? So they are based on, to a big extent, the way humans actually learn about images or get the ability to recognize images, right? So, for example, I tell my students, can you explain how you recognize a person's face? Do you use a formula for doing that every single time, right? Or is it instantaneous, right? So, so it's basically have neural networks that are trained on images, and the neural networks have a great discriminatory power. Over a period of time, after several years of looking at millions of faces, we become really good at identifying one versus the other, because our networks have very strong discriminative power in identification. And that's what these neural networks are trying to mimic. They're trying to mimic the human learning process of neural networks and trying to come up with a similar outcome. But they need large amounts of data to be good at that, right? And for us, every day when you walk from your home to your office, you already have a big training set, right? You're seeing large amount of individuals, you see faces of various shapes and sizes, various positions, and so you're getting better at that every single time. But with machines, we have to train them with all these kinds of images. So just to provide some information, in a traditional sort of machine learning approach, what we would do is, or data science approaches, if I wanted to be able to kind of recognize a dog, I would kind of extract features from images of dogs, and then I would actually run a classification algorithm on the data set that I've produced, and the classification algorithm would then help me identify a dog versus a boy or a bicycle, right? A deep learning approach, on the other hand, is slightly different in the sense that it is black box. So there is no model that has been learned that you can explain. But what you have are layers of networks through which when you feed data, different layers of networks are able to discern different features that can discriminate the dog from other kinds of objects. And based on the neural network then gives a probability for a particular example as being a dog or some other object. Right? So, but neural networks are out there and they are everywhere today. So, if you look at the industry, however, right, most industry users don't want black boxes because they need to explain their models to their clients. So, if you this is a survey, it's a little old, now 2011. But you find that decision trees or algorithms that learn decision trees from data are very popular from an enterprise or a business perspective, right? Black box approaches are good for certain kinds of things where you don't need to explain your models. They're not good for legal situations. They're not good in any situation where you have to actually explain your model to your client. Why is this model predicting or giving such an outcome, right? So if you need your models to have an explanatory power, neural networks are not going to help you there. But if you're not worried about explanation, for example, if all you care is about an autonomous car driving itself without crashing, it doesn't need to explain itself, then a black box approach is perfectly fine. And that's where neural networks excel in things like image recognition. I don't need a formula that tells me how I recognized your face. I just need to recognize your face, right? As long as I'm able to do that, the job's done. So in cases where you don't need that explanatory power, then neural networks are great. For all other things, we can look at traditional approaches. I don't know how many of you use some of these tools, but just to give you an idea about the vendor space. I mean, today we are completely spoiled for choice in data science, right? To be honest, you don't have to spend anything if you have the technical skill set. For example, there are a large number of open source tools that are basically of free cost, but of course there's the skill required for that, right? Then if you're looking at the vendor space itself, you find that there are, some of these vendors, for example, Tableau on the visualization has increased in leaps and bounds. Microsoft has several platforms, Google has several platforms, Amazon Web Services has several platforms. So there are a large. What I wanted to highlight to all of you is that you really can get away without spending too much money in the data science space. If all you're trying to do is get a proof of concept going, there's a large range of open source tools out there, and I would strongly recommend considering. There are several open source tools. In addition to that, there are programming languages which come with extensive packages and libraries of algorithms that you can use in testing your proof of concept solution. Right? So if you're short of funds, you should certainly consider the open source space, which is in fact some of the big data management tools that you might have heard of. I don't know if any of you have heard about Hadoop, for example, right? So Hadoop is a big data management framework which allows you to distribute analysis on large data sets. To put it in a very simple way, and Spark is another kind of, again, big data management framework that also includes machine learning algorithms, that also has support for streaming data, that does all of that. So, of course, you have to invest in the skill set, which is a challenge. So I'm not going to say it's very easy, but that is the same even for tools. Right? If you're going to invest in tools, you will need that investment in the skill set. Right? Just a few other things. So so far I've spoken to you about the traditional data science approach, where we have a structured data set, and you're trying to learn from the data set and come up with a model and use it for insights into the future, right? There's a whole other side to the other side of data science, which is based on unstructured data, and there we're looking at things like text analytics, multimedia analytics, right? So, for example, there's YouTube, for example, has a very big challenge of how do you automatically curate a video and publish it, right? So, to a big extent, there's no automated solution there, right? That can actually look at an uploaded video and automatically classify that video as something that is considered as decent media post or not, right? So there are no systems that can go through the video frame by frame and identify that, right? Because that's where AI is yet to grow. For example, there's no AI system that can you can easily fool an AI system to again predict a good video as a bad video and a bad video as a good one, right? It's because they are based on image recognition and so on. They don't have an idea of the context and all of that. So that is still an open challenge. Text analytics. So here's an interesting case study. So there's this challenge called the Reading Comprehension Challenge that happens every year. So Microsoft and Alibaba and a number of big companies, they take part in this. Samsung actually also takes part in this. They take part in this challenge where you have an AI algorithm that has to learn from lots of text and answer questions, right? So like what a high school student would probably do, memorize a lot of textbooks and then answer questions, right? So what they did was they did this. So this is a recent study where they tested, I think, 20 lawyers on identifying mistakes in non-disclosure agreements, right? So legal academics. I think they had about 20 people, 20 specialist lawyers, and what they got them to do was to actually look at non-disclosure agreements and identify mistakes in them. Right? So what they found was the LogX AI algorithm achieved a 94% accuracy, higher than the lawyers who were only able to achieve 85% accuracy in identifying mistakes. So the LogX algorithm was able to identify, but the best part is this. So it took 26 seconds on average for the LogX AI to run through the document and identify that, while it took the lawyers an average of 92 minutes. Right? I'm not saying that you can replace lawyers. I don't think you can ever replace them. But I think there's a case for automating at least a part of their task, and there might be cost savings for a lot of people that process. But what we're finding now is another big area for text analytics is, these are some of the applications, but a big area for text analytics is, let me move on, is what we call as sentiment analysis, right? You've seen this being, you probably have seen this being applied in a variety of contexts, in predicting elections or in trying to identify positive sentiment, voice of the customer, automated review analysis, restaurant reviews or reviews of any kind of thing. So what, to a great extent, what you find is 85 to 90% of all corporate data is in some form of text documents that are sitting on the intranet, right? If we can analyze them, and unstructured corporate data is doubling in size, so if we can tap into these information sources, I think we can. There's a wealth of knowledge to be ascertained from this. Not just that, even having the ability to extract knowledge of some kind from these unstructured corpus of data is a big thing that is more and more popular today. So sentiment analysis is just one application. There are other applications that we can use, and the goal is how do you try and identify what do people feel about a certain topic, right? So that's a key thing. I think one of the other big challenges that people are working on today is the fake news issue that I think organizations like Facebook are trying to work with. But I think it's Facebook detection algorithms have not yet reached the level of accuracy that you'd want them to. Right? So it is still a work in progress. Finally, this is something that is sort of also important. Elasticsearch is one of the is a technology that allows essentially superfast search of document files in diverse formats. So this is, if you look at a part of this data science process, finding information is a part of that process. So if you're trying to develop an end-to-end data science product, one of your key aspects would be to actually find information and then analyze it, right? So Elasticsearch is a technology that is an enabler for data science, that it allows you to actually quickly find documents, and it's a great information retrieval tool, and that is something that, again, based on open source technology, so just something that you can it's quite easy to invest in and very popular. And as an example, US federal government, for example, uses this to search and access data and documents on budget procurement from a variety of different agencies, right? So this is another important sort of enabler technology for data science. So just before I finish and wrap up, right? So just quickly to kind of again reiterate some of the issues that I see with data science and the challenges that face people, right? So this is a common kind of thing, that there's often there's more useless information than useful information anyway, right, out there. So how do you then deal with that, right? So the characteristics of data that we identified initially are also the challenges for data science projects, right? So I recently kind of again was looking at some data science work, and companies like Google, and there's another company called Glint AI. They are trying to come up with techniques that work with smaller quantities of data. How can you develop algorithms that would work well even when your data volumes are very low, right? So how can you come up with predictive models with low data volumes? I have seen several projects fail because of the, challenge in data integration. There are the data lies in a variety of systems. There are redundancies in the data. The cost of bringing the data together, it's not that it can't be done, but the project failed because the cost of data integration is much higher than what was the budget for the whole project, right? So, and I think one of the big disasters for IBM with Queensland government was also around this. I don't know if any of you are aware of that. I think it was a project which was quoted at 6 million, and it was, in the end, it was assessed to be 1.2 billion. I mean, this is one of the case studies we use as a failure of software engineering and what should be done in an ideal project. But from my memory of the case study, the reason it was underquoted was that IBM, this is what the Queensland government says, that IBM did not look at the difficulties of data integration, because data had to be brought in from a fragmented set of systems. So therefore, the cost of data integration shot to a large extent, and that was what kind of created an issue for them. But having said that, this is still a big issue that I find in many cases. And this is, I mean, we've had this problem to deal with when we worked on projects for clients with government agencies. Is that they don't have the ability to provide the data, and it's too expensive, or they don't have people that they can free up who can actually integrate the data for us. So the other thing is the streaming aspect. So the ability to process the data quickly as it comes through is another challenge. Challenge in the sense that the skill set is lacking in traditional enterprises to handle streaming data, right? I mean, all this data science field in the last 10 years, it has, the interest in the field has exponentially grown, right? Those software, the workforce before the last 10 years, I mean, I don't think many of them have any abilities to deal with streaming data, because that's just coming into we're just teaching about streaming data in the last few years. We've started introducing courses that for students that tell them how to handle streaming data, what kind of tools can they use, what techniques can they use. So how do you expect older software professionals to deal with those kinds of things? So skill set is a major challenge that I find. Data governance, I don't need to tell you about that. We're all aware of the data breaches that happen on a daily basis these days. So the issue is, how do you ensure security, privacy, and access? The data scientist issue is still there. How do you kind of identify and acquire good data scientists? And then the solution cost is often difficult to estimate in data science projects, because, for example, upfront it is often difficult to understand how much is it going to cost you to actually get the data together, right? What about if you need data from external sources beyond your enterprise? Then how do you deal with that? So the solution costs sometimes can be quite high in this context. Right? And lastly, and most importantly, I think the problem of algorithmic bias, which has actually in recent times, there's a lot of cases of algorithms, I guess, embedding some kind of bias or prejudice, which has to be eliminated, and that's something that you need to be aware of, right? Depending on the uses of your data science solutions. So again, these are the same things, but ultimately, these are common to any software engineering project. So it's not something that it's only common to data science. But I think the alignment between business and IT strategy, and actually having a clear business need for your data science solution is key, right? I mean, without that, all the other things I think are a waste of time. If you don't have those two, you're almost doomed anyway. And a typical data science workflow involves all these things, right? So a typical data science project would involve, a large amount of time spent in data wrangling, or acquiring data, cleaning it, applying tools to clean it as well, and you might have to then look at, if you're actually trying to solve your problems in a programmatic way, then you might need to actually create some kind of scripts that analyze this data, and the analysis needs to be reflected on, disseminated. So there's a number of other external aspects to this workflow, right, that also have to be taken into account. It's not as simple as automating the whole process. There are no tools out there that basically will do all your job for you. Take your data, automatically learn everything, give you a report at the end of it, right? There are some steps in that direction. For example, IBM Watson. I don't know, have you used this tool called IBM Watson or heard about it? Or, to a certain extent, that's what IBM Watson tries to do. That is, you upload a data set, and IBM Watson tries to do some analysis on the back end and tries to say, well, your data has so many missing values, its quality is bad, or it tries to do some pre-prediction on the data, right? And it lets you ask questions in English, so you can actually ask, what's the relationship between revenue and sales? So sort of revenue and basically say this quarter, right? So you can ask questions in English, and it tries to go back and analyze it, and it brings up these results. So more natural language kind of thing, but the human element is key here, and that's important to understand. Just to wrap up, and the recommendations, I've seen Gartner actually publish several research reports, and some of those reports have also outlined these recommendations. That is, have a specific list of objectives for your data science projects, right? what are the questions that you're trying to answer here, or what are you trying to predict in terms of the future? I mean, you can't take on a data science project as an abstract project where you say, let's try and see what we get from the data. That's not going to happen. It's much better going in by asking, listing a set of specific questions that you want your data to answer for you, right? That works much better, because then you know if your data can answer that or not, right? It's much clearer. Data is the key thing, so aim to provide the best and good quality data, and then you can stop if you can't find the data. So it's much better that way. There are tools that can work autonomously, but as I said, you can be diligent when you're investing in tools, because if you have the skill set, you can save a lot on tools, because there's a lot of open source availability there. And then finally, the domain expertise, right? Data scientists, many of them don't have domain expertise, so that I find is a big challenge, and then getting them to engage on the project. There are, again, these are some mistakes. You can have a look at them, with projects, commonly with data science projects as well. So just to wrap up, so point here is, I've given you a really brief overview of different data science things. I've shown you some videos and all of that, but it's a very, very kind of introductory overview of data science as such, right? But key thing to understand here is that there's a significant amount of investment going into data science today, into machine learning, and a lot of jobs jobs are at least being partially automated thanks to many machine learning techniques out there, right? So it's something that you're going to see explode in the years to come as techniques become more and more accurate and better algorithms come up. So key to understand is data is still the fuel, right? So if you invest in proper data engineering and data management, and that is most of your problem solved, right? So focus on the data. Machine learning can work fine if you have good data, good quality data, right? Many applications abound. So in fact, if you're in a particular industry, you'd find that there might be an existing solution already which has been deployed for that particular industry or for a particular kind of task that you're trying to achieve, right, or solve. So and then ultimately data science is not a single step, it's a process, right? So and the process needs to be followed to actually achieve the best results, right? So I'll stop talking now and let you ask questions.
Okay, so we've probably got about 10 to 15 minutes for
Sorry for
questions.
taking
No, that's fine.
time.
That's great. We've got about 10 to 15 minutes